Mrs. Peacemaker is a third grade teacher with 16 students at her local elementary school. She is taking her class on a field trip tomorrow, but there's a problem. Most of the kids in her class can't sit together at lunch or they'll get in a fight. She has some list of which kids get in fights with each other, and if she can see at least one other kid in between them, she can keep them from fighting. She was able to organize the list into a table, but it is still too complicated. How should the class be seated in order to prevent any fights from happening at lunchtime? Let me introduce Min Conflicts, a local search algorithm for constraint satisfaction problems. Basically, it's a step-by-step process for solving problems like these. It's actually pretty simple when you think about it. Step 1, pick a starting arrangement. Step 2, if there aren't any conflicts, then the problem is already solved. Otherwise, continue with Step 3. Step 3, choose one of the conflicting seats at random. Step 4, find the seat that the conflicting seat can swap with that will give the minimum number of overall conflicts. If there is a tie between two or more seats, we can just pick any one of them. Then you swap the seats. In Step 5, we repeat steps 2 through 5 until the problem is solved. So let's just start with everybody in alphabetical order. Let's look at Alan. He's sitting next to 3 kids, Bill, Dave, and Dan. If we look at Alan's list, we see that he gets in fights with Dan, but not Bill or Dave. So Alan only has one conflict. If we look at Jill, she is sitting next to 8 kids, Bill, Jack, Jeff, Joe, Sue, Sam, Kim, and Dave. If we look at her list, she gets in fights with Jack, Joe, Kim, Sam, and Sue, giving her 5 conflicts. After we look at all the kids, we get all of their conflicts and add them up to get the overall number of conflicts. We have 26 conflicts, so we have to continue with Step 3. We can't choose Jeff because he already has 0 conflicts, so let's choose Kim. In Step 4, we look at the overall number of conflicts there would be if Kim swapped seats with Alan, Bill, Dan, and so on, and we swap Kim's seat with whichever one will give us the lowest number. In this case, it's Jill. We now have 22 conflicts left. Step 5 takes us back to Step 2, and since there are still some conflicts, we repeat Steps 3, 4, and 5. We continue doing this until there are no more conflicts, and now we know where everyone should sit to avoid fights. This problem is just one specific example of a constraint satisfaction problem, and Min conflicts can be used on any problem dealing with constraints such as this one. It's important to note that this might not always give a solution for some problems, so if it looks like it's not working, you need to stop. You can try again with a different starting arrangement, or you can choose different conflicting seats along the way to try again for a solution. I hope you now realize how simple and powerful Min conflicts can be. Thank you and have a good day.